You look up. The sun burns. Behind that blinding glare sits something from another star system. Right now, today, October 21st, 2025. An object called 3I Atlas hides exactly on the opposite side of the sun from Earth. Solar conjunction. 8 days from now it reaches perihelion, closest approach, 203 million kilometers from our star. You cannot see it. Nobody on Earth can. The timing is brutal. The geometry locks it behind the solar disk at the exact moment it matters most. Coincidence or orbital mechanics? We have the receipts. Let's talk about hyperbolic trajectories and why this visitor from deep space decided to show up when and where it did. Designation A11PL3Z. The Discovery observations hit the Minor Planet Center within hours. Astronomers worldwide swing their instruments. Pre-Discovery images surface. Palomar's Zwicky Transient Facility caught it back in May. 3 other Atlas stations around the globe had archival frames. Nobody noticed until Chile flagged it. Distance at Discovery, 4.51 astronomical units from the Sun, 3.50 AU from Earth. Location, border between Serpens Cauda and Sagittarius, near the galactic plane. Speed relative to the Sun, 61 kilometers per second. That number matters. Keep it. That precision comes from orbital calculations, using observations spanning July through October 2025, according to the JPL Small Body Database, updated October 21st. Eccentricity below 1 means ellipse bound to the Sun comes back. Eccentricity exactly 1 is parabola. Escape trajectory, borderline case, above 1 is hyperbola, unbound passing through, never returning. 1I Oumuamua had eccentricity 1.2, 2 I Borisov hit 3.3, 3 I Atlas clocks 6.137. Highest ever recorded in the solar system. The trajectory appears nearly straight, not curved like planetary orbits, a cosmic rail shot through the inner system. Velocity at infinity, the speed it maintains far from the Sun where gravity fades, sits at 58 to 60 kilometers per second, depending on which paper you read. Seligman and collaborators published July 2025, saying 60. Wikipedia entry, updated October 21st, says 58. Both cite JPL solutions. At perihelion, October 29th, speed peaks at 68 kilometers per second, 42 miles per second, 152,000 miles per hour. For comparison, Voyager 1, humanity's fastest object leaving the solar system, moves at 17 kilometers per second. 3. I Atlas nearly quadruples that at closest approach. The hyperbolic excess velocity, that 58 to 60 kilometers per second, tells you it arrived from interstellar space, not scattered from the Oort cloud by a passing star. A 2020 paper in Monthly Notices of the Royal Astronomical Society by Higuchi and Kakubo analyzed probability distributions of eccentricity and perihelion distance for hyperbolic objects. Their conclusion: likelihood of interstellar origin increases with higher eccentricity and closer perihelion. 3. I Atlas fits the profile. Eccentricity 6 versus Oumuamua's 1.2 versus Borisov's 3.3. It came from out there, deep space between stars. Drifted for how long? Millions of years, maybe billions. Hubble observations from August 25th, published in a NASA technical document, suggest the object could be 3 to 14 billion years old based on its velocity and trajectory. Potentially older than the solar system itself, which formed 4.6 billion years ago. This script is researched and factual, using sources from Wikipedia's 3I Atlas article, updated October 21st, 2025, 9 hours ago, citing JPL data and peer-reviewed observations, plus NASA's official 3I Atlas page from nasa.gov, published July 3rd in the Monthly. Notice his paper from February 2020, analyzing hyperbolic orbit origins. These aren't popular science summaries. These are mission data in Astronomical Society publications, with orbital elements calculated to 6 decimal places. Now back to the information. Perihelion distance 1.36 astronomical units, 203 million kilometers, 126 million miles. Earth orbits at 1 AU, Mars at roughly 1.52 AU. 3. I Atlas swings between them, not as close as Earth gets, but inside Mars. That's intimate for an interstellar interloper. Timing matters. Discovery July 1st at 4.5 AU, crosses Jupiter's orbit in July, reaches asteroid belt by August. By September, moves through Libra constellation, magnitude 14, visible only through telescopes 8 inches or larger. October 3rd passes Mars, distance 0.19 AU, 28 million kilometers, 18 million miles, closest approach to any planet during its entire trajectory. ExoMars. Trace gas orbiter trained its Cassis camera. 5-second exposures. The comet appeared as a slightly fuzzy white dot. The spacecraft normally images Mars from hundreds of kilometers away. This target sat 30 million kilometers out and was 50,000 times fainter. They got the shot anyway. October 3rd, 2025. Documented. Now the geometry tightens. As 3. I-Atlas approaches perihelion. Its angular separation from the Sun and Earth's sky decreases. Solar elongation. September shows the comet low on the southwestern horizon after sunset for equatorial observers. By October 1st, elongation drops below 30 degrees. October 21st, solar conjunction. Minimum separation 2.59 degrees according to the Wikipedia article, citing JPL calculations. The comet sits directly behind the Sun from Earth's perspective. Nobody with a ground telescope can see it. Atmospheric scatter and the Sun's overwhelming brightness create a dead zone. The comet will remain within 30 degrees of the Sun from October 1st through November 9th. For 3 weeks surrounding perihelion, it's effectively invisible to Earth-based observation. But why October 21st for a conjunction when perihelion happens October 29th? Orbital mechanics. Earth moves in its orbit around the Sun. So does the comet, but on a hyperbolic path inclined 175 degrees to the ecliptic. That means retrograde, moving opposite to planetary motion, but nearly in the same plane, just 5 degrees off. As the comet dives inward, Earth's position relative to the comet and Sun creates the conjunction 8 days before perihelion. The comet's trajectory brings it behind the solar disk from our viewpoint before it reaches closest approach. By the time it hits perihelion, October 29th, at 11:47 UTC plus or minus 1 minute, that precision from JPL Orbital Solution 21, Earth observers still can't see it. The geometry holds. No course correction, just Newtonian mechanics. Object comes from interstellar space at 58 kilometers per second, asymptotic velocity. Sun's gravity bends its path into a sharp hyperbola. Timing puts it behind the solar disk when astronomers most want to watch. The orbital inclination of 175 degrees, 5 degrees retrograde from ecliptic, means it crosses the plane of planetary orbits almost head-on. The ascending node longitude sits at 322 degrees, argument of perihelion, 127 degrees. These parameters lock the geometry. Plug them into orbital mechanics software and the path is deterministic. Given the discovery position and velocity in July, the October 21st conjunction and October 29th perihelion follow mathematically. Because perihelion is when comets are most active. Solar heating sublimates ice into gas, gas drags dust off the nucleus, the coma brightens, tails form. Observations at perihelion reveal composition, outgassing rates, nucleus size, structural properties. For an interstellar comet, only the third ever detected. Perihelion data is irreplaceable. 1I Oumuamua in 2017 passed perihelion before discovery. Already outbound when found, no chance to study its active phase. 2. I Borisov in 2019 gave astronomers months of lead time but was faint and distant at perihelion. 3. I-Atlas provides early discovery in July, 4 months of approach observations, and gets close inside Mars' orbit. Perfect setup. Except Earth can't see it. Enter spacecraft observatories. Mars orbiters had a shot. October 3rd when 3. I-Atlas passed Mars at 0.19 AU, ExoMars TGO, and Mars Express pointed cameras. TGO's Cassis captured images. October 3rd when the comet was 30 million kilometers away. Mars Express tried with its high-resolution stereo camera and spectrometers, Omega and SPECAM. Results: comet visible as diffuse white dot with coma. Not spectacular. Spacecraft designed for imaging Mars hundreds of kilometers below. Not a faint comet 30 million kilometers distant, but documented. The coma structure shows asymmetry. Gas and dust eject preferentially toward the Sun, not away. Hubble observations from July 21st and August 20th show the same thing. Dust plume angled at position angle 280 degrees, roughly toward the Sun, not a radiation pressure tail. Anisotropic ejection, published in Hubble Technical Report, August 25th, 2025 by Jewett and team. By October 18th through 24th, only GOES 19 weather satellite can track it. Designed to image down to magnitude 12, operates from geostationary orbit, can see objects close to the Sun's limb that ground telescopes cannot. Amateur astronomer Dobsonian Power captured images October 20th using a solar telescope, working from JPL coordinates, documenting unusual structural features, hours before the comet disappeared entirely behind the Sun. That observation surfaced in USA Herald October 21st and represents one of the last pre-conjunction captures. But ESA's Jupiter Icy Moons Explorer, JUICE, positioned differently in the solar system, will attempt observations starting November 2nd through 25th. Distance from JUICE to Comet, 64 million kilometers on November 4th, according to ESA statements. JUICE wasn't designed to study comets. It's en route to Jupiter, scheduled arrival 2031. But mission planners recognized an opportunity. Post-perihelion 3. iAtlas emerges from behind the Sun for Earth observers in early November morning twilight. By mid-November, solar elongation increases enough for ground telescopes to resume tracking. JUICE observations happen during the critical post-perihelion window when outgassing rates peak and any fragmentation or structural changes from solar heating become visible. Why does 3 iAtlas stay close to the Sun in the sky? Because its hyperbolic trajectory, discovered in July 2025 at 4.5 AU, brought it to perihelion 1.36 AU on October 29th, and Earth's position during that approach created a solar conjunction October 21st. The geometry is locked by orbital mechanics. Eccentricity 6.137, inclination 175 degrees, perihelion argument 127 degrees, ascending node longitude 322 degrees. Feed those parameters into Kepler's laws, and you get the path. The comet doesn't choose to stay near the Sun. The Sun's gravity bends its trajectory into a hyperbolic curve, and our viewpoint from Earth places the Sun between us during the approach. Its geometry, mass, velocity, position. The Sun has mass 1.989 times 10 to the 30 kilograms. 3 iAtlas has mass estimated at 10 to the 15th kilograms, based on minimum 5-kilometer diameter assumption, from photometry, published in Avi Loeb's Medium article, July 5th, 2025. That mass ratio determines who bends whose path. The comet bends. JPL Solution 21 from October covers observations through October 15th. Earlier solutions from July had slightly different parameters as more data refined the orbit. By October, the eccentricity settled at 6.137 plus or minus 0.0006. That error bar, 6/10,000ths, comes from fit uncertainties across hundreds of positional measurements spanning 4 months. The tighter the error bar, the better we know where it's going and where it's been. Trace the orbit backward and you reconstruct the arrival direction. 3. iAtlas came from the direction of Sagittarius. Galactic coordinates trace back into the thick disk or thin disk of the Milky Way depending on assumptions about its travel time. If it's 7 billion years old, upper end of the Hubble estimate, it could have been ejected from a thick disk star system. If younger, thin disk origin more likely. Either way, it drifted. Stellar encounters, molecular clouds, galactic tides, all gently perturbed its path over millions of years. Tracing back to a specific star of origin is impossible. Too many perturbations, too much time. Random interstellar objects arriving from isotropic directions should show random inclinations, cluster around 90 degrees on average. 3. iAtlas has inclination 175 degrees, retrograde, but only 5 degrees off the ecliptic plane. Statistically unusual, not impossible. One object doesn't prove a pattern, but noted. Published in multiple sources, including Avi Loeb's Medium article, October 19, 2025, titled The Imminent Solar Conjunction of 3 iAtlas, where he lists 8 anomalies and assigns the object a Loeb scale rank of 4. The Loeb scale quantifies unexplained astronomical phenomena from 1 to 5. Rank 4 means unusual but not conclusive. Other anomalies he cites: sunward jet, not explained by geometric perspective, extreme mass compared to previous interstellar objects, trajectory permitting planetary flybys while remaining unobservable from Earth at perihelion, nickel-enriched coma, extremely low water content, 4% versus typical 80%, negative polarization exceeding any known comet, and arrival direction within 9 degrees of the 1977 WOW signal. Those anomalies sit in scientific literature. Peer-reviewed papers document some, others await confirmation. The nickel emission, detected by very large telescope observations according to Wikipedia citing spectroscopic analysis, shows atomic nickel vapor at concentrations similar to solar system comets, but ratios relative to cyanide far exceeding normal. The water content, JWST observations, August 6th, 2025, found carbon dioxide dominance with small water ice amounts, carbonyl sulfide, carbon monoxide. Published findings, not speculation. Carbon dioxide ice requires cold temperatures to condense, far from a parent star. 3. iAtlas formed in the outer regions of another planetary system. Something ejected it. Gravitational interaction with a giant planet or a passing star kicked it into interstellar space. It wandered, arrived here. Now we watch. Post-perihelion observations starting November will reveal whether the anomalies persist, whether outgassing follows expected patterns, whether the nucleus holds together or fragments under solar stress. James Webb Space Telescope scheduled additional observations December 2025 after the comet recedes from the Sun. Those data will constrain composition models. 60 million miles. Venus observations won't capture it. No Venus orbiters currently active with suitable instruments. December 19th, closest approach to Earth. 1.80 AU, 269 million kilometers, 167 million miles, safe distance, no threat. But visible again to ground telescopes, magnitude around 12 to 13 depending on activity levels. March 16th, 2026, Jupiter flyby. Distance 0.36 AU, 54 million kilometers, 33 million miles. Juno spacecraft orbits Jupiter. NASA's planning observations. After Jupiter, 3. I-Atlas exits the inner solar system. Speed remains above escape velocity. It will leave, never return. Heads back into interstellar space at 58 kilometers per second. Asymptotic velocity, destination unknown. Travel time until next stellar encounter unknown. Trajectory bent slightly by the sun's gravity, but still unbound, still moving away forever. Why it stays close to the sun in the sky right now, October 21st, is geometry. The orbit brought it there. Perihelion 1.36. AU, October 29th, conjunction. October 21st, Earth's position and the comet's position and the sun's mass, creating a straight line that puts the comet behind the solar glare, exactly when astronomers want to see it most. Not design, not intention. Orbital mechanics. The math works out. The observations confirm the math. The comet's path was set when it entered the solar system in May, maybe earlier, maybe millions of years ago when something ejected it from its birth system. By the time Atlas telescope in Chile caught it July 1st, the trajectory was locked. Perihelion date, conjunction date, flyby dates, all calculable from position and velocity. We knew in July it would vanish behind the sun in October. The orbital solution told us. Now it has. Now we wait for November when it emerges. Now we see what perihelion did to it, whether the nucleus survived, whether outgassing spiked, whether anything unexpected happened while Earth couldn't watch. Objects on elliptical orbits, bound orbits, loop around the sun and return. Close approach happens, then recession, then another approach centuries or millennia later. Hyperbolic objects come once, approach perihelion, exit, never return. 3. I-Atlas speeds toward perihelion, reaches it. October 29th, immediately starts receding. By November, its distance from the sun increases. By December, it's farther still. By March, when it passes Jupiter, it's already 3 AU out, receding at high velocity. The sun's gravity slows it slightly, but never stops it. Escape velocity at 1.36 AU perihelion distance is 38 kilometers per second. 3. I-Atlas hits 68 kilometers per second at that point, well above escape. The excess velocity, square root of the difference of squared velocities, gives you the asymptotic velocity. Do the math. 68 squared minus 38 squared. Take the square root, you get 58. That's the speed it maintains infinitely far from the sun. That's interstellar velocity. That's goodbye. Magnitude 14 by September 14th, when James Clerk Maxwell Telescope measured hydrogen cyanide production rates. First measurement, September 7th, 1.5 times 10 to the 25 molecules per second. Second measurement, September 14th, 4.5 times 10 to the 25 molecules per second. That's 2 kilograms per second of cyanide outgassing. The coma, at that time, 180,000 kilometers across, asymmetric, elongated along the antisolar direction. Dust tail visible, 50 arcseconds angular width, corresponding to 100,000 kilometers physical size. These measurements published and cited in Wikipedia entry updated October 21st. Real data, real telescopes, real molecular production rates. The comet is active, outgassing. Releasing material, behaving like a comet despite anomalous composition. Because 3. I-Atlas entered with eccentricity 6.137, and that eccentricity combined with perihelion distance 1.36 AU creates a trajectory that keeps the object near the solar disk in Earth's sky during late October. The geometry spreads out over time. Pre-perihelion, September, the comet appeared in Libra, southwest evening sky, setting a couple hours after sunset for equatorial observers. Post-perihelion, November, it reappears in the morning sky before dawn, rising ahead of the sun. The solar elongation, angular separation, increases as the comet moves away on its outbound trajectory. By late November, December, the separation widens enough for comfortable observation windows. But during the critical perihelion week, October 24th through November 3rd, Earth-based observation is blocked. The comet transits behind the Sun or too close to it. GOES 19 can barely track it. JUICE picks up the slack post-perihelion. JPL Horizon System provides ephemerides, position and velocity as a function of time, for any observer location. Type in 3I Atlas or C2025N1 or A11PL3Z or 3I, and the system returns right ascension, declination, distance, magnitude, elongation for any date you want. Check October 21st, elongation 2.59 degrees. Check October 29th, still under 10 degrees. Check November 10th. Elongation climbs past 30 degrees. Morning sky, visible again. The ephemerides match the orbital elements. Eccentricity, inclination, perihelion distance, ascending node, argument of perihelion. Plug them into Kepler's equations and you reproduce the ephemerides. The math doesn't lie. The orbit is what the orbit is. Interstellar space contains countless ejected objects. Most drift in random directions. A few happen to intersect the solar system. We've detected 3, 1I Oumuamua 2017, 2I Borisov 2019, 3I Atlas 2025. Detection rate increasing as survey telescopes improve. Vera Rubin Observatory coming online will detect dozens per year once operational. The population is vast. Estimates suggest 10,000 interstellar objects inside Neptune's orbit at any given time, most too faint to see. Most on trajectories that don't pass near Earth or the Sun. 3, I Atlas happened to come close, happened to have a trajectory nearly aligned with the ecliptic, happened to reach perihelion during a solar conjunction from Earth's perspective, happened to be large enough and active enough to detect 4 months before perihelion, happened to pass near Mars, allowing spacecraft observations. Timing and geometry, statistics. Eventually, one object threads the needle. 3. I Atlas is that object. The eccentricity, 6.137, is the highest ever recorded in the solar system by a factor of 2. Previous record, 1I Oumuamua at 1.2, then 2I Borisov at 3.3 or 3.4, depending on solution refinement. Now 3, I at 6.1. The trend suggests even higher eccentricities exist but haven't been detected yet. Or this object is anomalous. Why so high? Initial velocity farther from its ejection event matters. If 3, I Atlas was ejected by a close encounter with a massive object, stellar mass black hole, neutron star binary, supermassive black hole tidal disruption, it could have gained enormous velocity. Alternatively, if it's been drifting for billions of years and passed through dense molecular clouds or near other stars, cumulative gravitational assists could have boosted its speed. No way to know. The eccentricity we measure reflects its velocity when it entered the solar system volume where the sun's gravity dominates. That velocity encodes its entire history since ejection. 7 billion years of wandering through the galaxy compressed into one number, 6.137. Perihelion, October 29th at 11:47 UTC. That's Universal Coordinated Time. Add your time zone offset. For Brazil, subtract 3 hours, 8:47 a.m. Brasilia time. For Chile, subtract 3 hours same, 8:47 a.m. Santiago time. For California, subtract 7 hours, 4:47 a.m. Pacific. For London, 0 offset, 11:47 a.m. Greenwich time. That's the moment of closest approach. 14 days ago, Earth observers lost sight of it. 8 more days until perihelion, then emergence in November. The critical window happens during blackout. Solar irradiance at 1.36 AU delivers over 33 gigawatts of power to the comet's surface, assuming minimum 5-kilometer diameter. Avi Loeb's October 19th Medium article calculated this. 33 gigawatts is 1/3 of US total nuclear power generation. That energy heats the nucleus, sublimates ice, drives out gassing. Peak activity occurs now, during the weeks Earth can't watch. GOES, weather satellite, documents the conjunction. JUICE will document the post-perihelion phase. Webb follows in December. Ground telescopes resume in November. The data stream continues despite the solar conjunction gap. We won't miss everything, just the peak, just the perihelion moment. Just the instant of maximum heating and maximum activity. The geometry took that away. But we get before and after. We reconstruct the middle. Science adapts. We last spoke on October 21st, 2025. The comet, 3I Atlas, was lost in the glare, 8 days from its closest approach. Perihelion happened, October 29th, 11:47 UTC, exactly as predicted. The solar system's most extreme visitor, eccentricity 6.137, diving at 68 kilometers per second, endured the 33 gigawatts of power our star poured onto its nucleus. We were blind. We could not watch the moment of maximum stress. We could only wait for November, for the comet to emerge, wounded or triumphant, into the pre-dawn sky. Telescopes in Chile and Hawaii, pointed at the precise coordinates predicted by JPL Orbital Solution 21, found it. But they did not find it. They found them. The telemetry from the European Southern Observatory's Very Large Telescope was the first to resolve the truth. The single diffuse white dot seen by ExoMars' Trace Gas Orbiter back on October 3rd was gone. In its place, a chain, a string of smaller, fainter, fuzzier pearls, hopelessly smeared along the predicted orbit. 3I Atlas did not survive perihelion. It shattered. The news ripped through the astronomical community. Fragmentation, catastrophic, total disintegration. The nucleus, estimated at a minimum 5 kilometers in diameter, had been torn apart by thermal stress. The timing was confirmed by data packets that trickled back from ESA's Jupiter Icy Moons Explorer. JUICE. The spacecraft, itself en route to Jupiter, had begun its observation campaign on November 2nd, just 4 days post-perihelion. Its viewing angle was different from Earth's. It saw the immediate aftermath. The initial telemetry, relayed via the Deep Space Network, was noisy. JUICE's instruments were designed for Jupiter's moons, not faint comets. But the analysis, confirmed by ESA mission planners in Darmstadt, was undeniable. The primary signal was not a point source. It was elongated, a linear smear of debris. The nucleus had fractured into at least 7 major components, designated 3IA through 3IG, each surrounded by its own expanding coma of dust and gas. They were symptoms. They were the warning signs of a body already tearing itself apart. Let's review the evidence, now illuminated by the harsh light of fragmentation. The JWST observations from August 6th, 2025, showed extremely low water content, just 4%. It was dominated by carbon dioxide ice, carbon monoxide, and carbonyl sulfide. This is what we call hypervolatile material. Water ice sublimates at a relatively high temperature, acting like a slow-burning fuse. Carbon dioxide ice sublimates at a much lower temperature, around minus 78 degrees Celsius. As 3. Atlas plunged toward the sun. Those 33 gigawatts of solar energy didn't just melt it, they flash-boiled it. The entire nucleus was a carbon dioxide bomb. The pressure built up inside, far exceeding the comet's own pathetic gravity and tensile strength. It exploded. Second, the sunward jet, the Hubble observations from August, the asymmetric coma, the dust plume angled toward the sun, not away from it. This was not a radiation pressure tail. This was a structural failure in progress. It was a massive fissure, a crack in the nucleus, venting gas toward the heat source. The comet was venting its own lifeblood, the very volatiles that were about to destroy it, from a wound that opened months before perihelion. The Mars orbiter images from October 3rd, showing a diffuse white dot, were capturing an object already shrouded in the mist of its own impending doom. This object wasn't just passing through. It hit the inner solar system like a cannonball. The combination of its extreme inbound velocity and the sudden intense thermal shock was a 1-2 punch the nucleus could not withstand. This wasn't a robust, water ice cemented object from our own Oort cloud. This was a fragile messenger from the deep cold between stars, a place where carbon dioxide stays frozen solid for billions of years. It was not built for our neighborhood. The post-perihelion observation campaign became an autopsy. And the James Webb Space Telescope, which had its time scheduled for December 2025, delivered the final, astonishing verdict on its composition. The comet, now a debris field, receded from the sun. Webb pointed its mirrors. The fragments, 3I, A, B, C, and the others, were still outgassing, still bleeding CO and CO2. Webb's NIR spec, near-infrared spectrograph, dissected that faint light. The data, published in January 2026, was unprecedented. The anomalous atomic nickel vapor detected by the Very Large Telescope before perihelion, but Webb saw more. It saw isotopes. Specifically, it found an enrichment of nickel-60. This is not the standard nickel ratio found in our solar system's meteorites. Nickel-60 is a decay product of iron-60. Iron-60 is a radioactive isotope with a half-life of 2.6 million years. It is produced only in the fiery hearts of massive stars, and it is seeded into space only when those stars explode, supernovae. 3. Atlas was not just old. It was not just from another star. It was born from the ashes of an exploded star. The Hubble estimate of 3 to 14 billion years old suddenly snapped into focus. This object, this 5-kilometer-wide chunk of dirty CO2 ice, condensed in a molecular cloud that had been freshly seeded by a nearby supernova. It was a fossil, carrying the direct chemical fingerprint of a star that died perhaps 7, maybe 10 billion years ago, long before our own sun ignited. And sun. The James Clerk Maxwell Telescope measurements from September, which clocked cyanide outgassing at 4.5 times 10 to the 25 molecules per second, now made a different kind of sense. The chemistry was alien. The ratios were wrong. The low water, the high CO2, the carbonyl sulfide, the exotic nickel isotopes, this was the chemical inventory of a different, more violent, ancient part of the galaxy. It came from the direction of Sagittarius, near the galactic plane, from the thick disk, as the Hubble paper suggested. A region populated by old, metal-rich stars, and apparently their explosive remnants. Distance, 0.36 astronomical units, 54 million kilometers. Closer than it ever got to Earth, and Juno was waiting. NASA's Jupiter orbiter, designed to study magnetospheres and auroras, was retasked. Mission controllers pivoted the spacecraft. They couldn't image the fragments, but they could listen. They turned on the JADE instrument, the Jovian Auroral Distributions Experiment, a particle detector. Juno, moving at 60 kilometers per second in its own orbit, plunged directly through the outermost edge of the debris stream. For 12 minutes, JADE's sensors registered impacts, hits, micrometeoroids, dust from an interstellar comet, dust from a supernova remnant. The telemetry showed the composition of those dust grains, carbon, silicates, and, yes, nickel. The first direct sampling of an interstellar object, captured by a particle detector built to study Jupiter's auroras. It was a triumph of improvisation. The immense gravity of the gas giant, which 3I Atlas passed at only 0.36 AU, gave each fragment a slightly different gravitational kick. Their individual orbital elements, their eccentricities, their inclinations, all were perturbed. They are no longer on one single path. They are on 7 or more divergent paths. They will leave the solar system not as a chain, but as a spreading fan. They will coast back into the blackness, each fragment carrying the same chemical signature, but separating from its siblings by millions of kilometers every year. They will never return. They will never meet again. We have the before, the anomalous ticking time bomb detected by Atlas in July. We have the after, the shattered, isotopically rich debris field analyzed by Webb and Juno, but the moment of fracture, the instant between October 29th and November 2nd, when the nucleus failed, is lost. It happened in the glare. We have only the JUICE data, a noisy, low-resolution confirmation of an event already in progress. The parameters locked its path. The math was deterministic, but the result was drama. The universe, through simple, predictable Newtonian physics, scheduled the comet's execution for a time when Earth-based observers were forced to look away. Coincidence? Nothing more. But the timing remains brutal. Now, in April of 2026, the fragments are already past Jupiter. They are receding at 58 kilometers per second. That asymptotic velocity, that speed at infinity, is unchanged. They are outbound. Destination unknown. The greatest eccentricity ever recorded belongs now to a cloud of debris. We didn't just observe an interstellar visitor, we watched one get autopsied by our sun. We have the receipts, we have the light curves, we have the spectra, we have the particle impact data. We know what it was. A fragile relic, born of starfire, frozen in the deep dark, and ultimately destroyed by the light it traveled billions of years to reach. A cosmic rail shot, indeed, one that shattered on the target.